When we combine our functions, what does the domain of this new function look like? And we're going to just talk about domains for now because ranges can get tricky. For x to be in the domain of the sum, difference, product, or quotient of two functions, f and g, we need to be able to do three things. We need to be able to evaluate f, so that means x is in the domain of f. We need to be able to evaluate g, so that means x is in the domain of g. And then we need to be able to do whatever the appropriate operation is, add, subtract, multiply, or divide. Now, we can add or subtract or multiply any two numbers, right? Any numbers you think of, you can add them together. You can subtract them, might get a negative answer. You can multiply them. But there's one specific number that doesn't work in division. Specifically, we can't divide by 0. 0 divided by something, that's fine. But something divided by 0, that doesn't work. So this tells us what it takes to be in the domain of these new functions. For adding, subtracting, and multiplying, these are all we need. For dividing, we also need to not divide by 0. And that's it. As long as we can do f, we can do g, and we can do our arithmetic, we're in the domain of the new function. To state this formally in notation, the domain of the sum, difference, and product is just the intersection of the domains of our original functions. The domain of the quotient has to do that, so the intersection of the domains of the functions, and also the function in the denominator can't be 0. Remember, numerator 0 is fine. It's denominator 0 that we can't have. So just as a basic example, suppose that we have a function f whose domain is negative infinity up to 3, and a function g whose domain is negative 6 up to 15. So the domain of the sum, difference, and product is just the intersection of these two sets. To help us see what that intersection is, let's just kind of make a rough sketch of a number line. The interesting numbers we have are negative 6, 3, and 15. The domain of f has a filled in dot at 3 and includes all the numbers to the left. The domain of g has an empty dot at 6 and 15 and includes all the numbers in between. And so the intersection will have an empty dot at 6, a filled in dot at 3, right? The intersection, we're just looking at the overlap. So the intersection will just be the numbers negative 6 up to 3. Just the intersection of the two domains. What about the quotient? Suppose we also know that the solution set of g of x equals 0 is negative 2 and 1. This means that g is only 0 when x is negative 2 or x is 1. Well, looking at this sketch again, negative 2 and 1 come in between negative 6 and 3. So we're going to think of that as just punching holes in this domain at negative 2 and at 1. So the domain of our quotient function is going to be negative 6 up to negative 2, and then there's a little hole, negative 2 up to 1, another little hole, then 1 up to 3. And the reason we had to write this as this union of 3 sets is that -2 is not in the domain, and 1 is also not in the domain. So that's it, right? Domain of the sum, difference, and product is just the intersection of the two domains. The domain of the quotient also excludes any points where the output in the denominator is 0.